So our project is the design and analysis of a thin-walled tube cutting process. There we go. So sort of a quick background. The company I worked for was it developed and manufactured intravascular imaging catheters. And common materials in catheters are plastics because they're lightweight and easy to manufacture. And PEEK in particular is a very common plastic tube used in them. And commonly the main use of these tubes is basically as a transfer, a load transfer shaft. So they're the way they're cut and the tolerances to which they're cut have to be precise and clean, so that the connections between those parts are precise and they're aligned well. So for our purposes, we're going to look at a tube that's about 1 millimeter in diameter, and it has a wall thickness of about 6 thousandths. The length tolerance, which is somewhat standard in the catheters that we produce, is about 1/16 of an inch. The ends of the tubes need to be cleanly cut. The tube cannot be deformed, so those are the constraints, and the process needs to be low cost and time efficient. So the idea of this project is sort of what I explained before, to create a process to precisely cut tubes in a time efficient and low cost manner. The real challenge here is creating a repeatable process to cut them because of their fragility and just basically how small they are and how easily they are to kink and deform. So we looked into some of the standard methods of cutting tubes, and there's sort of a chopping method and rotating blade, and you can spin a lathe, and there's laser cutters. And a lot of times when you're dealing with the tiny tubes, they kind of fray the edges when you cut them if you don't do it extremely precisely, especially after there's been a pass on the blade. So Steve will talk about decomp.
So first we broke down our major FR0 of cutting thin-walled PEEK tubing into the 3 main components. We went with a systematic theme to this. So we first figured we had to mount the tubing, then we had to cleanly cut the tubing, and then we had to remove the cut tubing. The DPs that went with these respectively are a method for securing the tube, method for cleanly cutting, and a method for removing the finished tube. So breaking down FR1, we figured in order to mount the tubing, we had to control the movement of the tubing and support the inside of the tubing. And to control the movement of the tubing, after some iterative processes, we came down with these 4 solutions of just limiting it in the X direction, the Y direction, while controlling the movement in the Z direction and controlling its rotation about the Z axis. Because it was determined that if we were able to rotate it instead of rotating it around rotating the cutting tool. But we canceled that after looking into FR2. We decided to support the inside of the tubing. We broke that down into support the stiffness of the tubing to provide a slip surface, provide a slip fit, and provide a sliding surface. The point of this was to put a mandrel inside the tube to give it support so when we cut it, nothing came down or crushed or happened to block the inside of the tubing, depending on what method we used to eventually cut the tube. And the slip fit provided the clearance so we could slide the tube in, so we could slide the mandrel in and out of the tube. Our FR0 cleanly cut the tubing. We wanted to provide a square cut, so we wanted a nice flush end that we could use to mount the tube. Then we had to provide a repeatable and quick cut, so we needed to determine a method to cut in both those manners. So we decided to use, for a repeatable cut, we used a computer guidance system, and we knew with that computer guidance system we'd have a slight error in what it would cut every single time. And for the quick cut, we decided on a laser cutting system. And with that, we figured we could hone the tip of the laser in its focus area, so it would only cut the tubing and not cut the mandrel inside the tube. And as well as we had to provide a 360-degree cut. So that's where we came up with a device that rotates the tubing while it's being cut. So we had something spinning the tube on its z-axis while the laser just stayed pointed at the one position. And our FR3 was remove the cut tubing. And what we had this was push the tubing off supporting device. So with that, we had a stepper motor that slowly pushed the tubing from the back end up at set intervals that the computer controlled and eventually pushed it off the edge of the mandrel. And then we controlled where the tubing gets deposited, and that was just we tapered the end of the mandrel so it nicely fell into a device underneath the entire surface. Here's our complete decomposition with all the different breakdowns. And for our FR versus DP matrix, comparing them, we realized there was a few occurrences where they happened, and that was at our FR 2.3 and our FR 3.1, just instances where we were controlling the motion of the tubing and what the mandrel and the stepper motor were doing with the device.
So how we physically integrated this, we talked about a little bit in the decomposition, but the first step in the process would be to load the tube onto a mandrel into a fixture, and then we want to engage the tube with a computer-controlled guidance system so that would be able to manipulate the location of the tube. And we want to load the tube into a set cutting position and begin rotating the tube that will also be controlled by the computer system. And then we will be able to cut the tube, and then after we cut the tube, we would push the tube off by moving the original tube back into the new loading position, and that'll slide off the tapered end into another device. And then this process will go on and on until you get the desired number of cut tubes that you need for manufacturing or for your assembly. In conclusion, we have there was some coupling, but it's a decoupled system. We think that we were able to achieve CME-min, and we think that the sum of the children equal to parents, and we think we had an innovative technology that could be used. So, thank you for your attention.
All right, questions? How did you decide on a mandrel?
We decided on a mandrel because we thought it would be a good way to be able to slide the tube off at the end of the process. But that was one of the reasons we decided to do that.
I can see the potential. I worked for a medical device company over the summer.
Sure.
Stainless steel, small tubes.
Sure. Sure.
And I ran multiple tests on it, and what would happen is if the tube was too thick, it would clog in on itself against the laser, and it wouldn't actually have the material.
Right.
So the mandrel would allow you to actually get rid of the material that you're trying to cut.
Right.
So why wouldn't you, instead of using mandrel, use high pressure gas or liquid, basically support the tube as you cut?
Yeah. Certainly, it would be something we'd have to take into consideration during that iteration.
Hold on a second. Jeff?
I was just wondering, what are my material using? Is there any possibilities like melting or deforming with laser?
If you use the right laser, I know that peak tubes have been laser cut before, so I don't foresee that being an issue. But that's a good point to bring up.
I was just wondering.
Yeah. No, it's a good point. Right. We thought of that, and we thought that might involve rotating the fixture, and we thought that rotating the fixture might cause more problems than rotating the part itself. But that's a good consideration.
Could you go back to the matrix? I'm glad people are doing the matrix.
All right, so the thing I want to go back to here is if the children are coupled, the parents are coupled. And if we see coupling at one level, at a high level, we should be seeing the origins of it at a low level. It's kind of hard to follow in the matrix, and I've suggested to ADSI that they do a better job with this. But if, so it goes, DP1 is coupled somehow with FR2.3. So that's the fixture for controlling something.
That means,
Provide 360-degree.
yeah, provides a 360-degree cut.
Now,
So-
DP1 is decomposed here, so that someplace along DP1, we've got a z-axis rotation is coupled. Right?
Yeah.
So this coupling is inherited here, right?
Hmm?
Right. So if 2.3 is coupled with 1.1, shouldn't 2 be coupled with 1.1?
Okay.
And if 1.1 is coupled with 2, then 1 should be coupled with 2. Because
Okay.
if the sum of the children equals the parent, and there's coupling down here, that coupling needs to be inherited.
Okay.
See that?
Yeah.
And I had a slide or two on that when we talked about coupling and using the matrix.
Right.
So this implies something up here. But also, if you have the higher level coupling, you should be able to trace it. One of the reasons you want to trace it is so that you could possibly eliminate it.